Welcome to this new online tutorial in bioprocess engineering, digital scale-up of microbial fermentation on spreadsheet. In this tutorial, we focus on the second part of the scale-up process for fed batch operations, dedicated to the optimization of fed batch fermentation strategies. In the bioprocess engineering online tutorial series, I present the fundamental principles and industrial applications of bioprocess engineering. I particularly highlight the power of spreadsheets for performing key bioprocess engineering tasks, including analyzing experimental data, modeling and simulating bioreactors, scaling up and optimizing bioreactors, designing integrated bioprocesses, evaluating economic and environmental performance, and performing sensitivity and uncertainty analyses. In this new tutorial series on the digital scale-up of microbial fermentations, we focus on scaling up microbial processes from the laboratory scale to industrial fermenters, considering batch, continuous, and fed batch modes of operation. The series emphasizes digital scale-up using mechanistic, knowledge-based models to predict process behavior across different scales. These models act as digital twins, virtual representations of fermenters, enabling in silico experimentation under a wide range of operating conditions. Unlike empirical approaches, they allow virtual testing before implementation, thereby reducing costly pilot-scale trials and accelerating process development. In this tutorial, the digital scale-up methodology is illustrated through a case study on the fermentation of baker's yeast, Saccharomyces cerevisiae, progressing from laboratory scale to an industrial 100 cubic meter fermenter. The yeast fermentation is carried out in fed batch mode, in which only part of the sugar is initially introduced into the fermenter, while the remainder is continuously fed to maintain a low glucose concentration. Unlike batch operation, where large amounts of ethanol are produced during yeast growth, these sugar-limited conditions strongly reduce ethanol formation. The first part of this tutorial series on the digital scale-up of fed batch fermentation presented the development of a simulation model for yeast-fed batch fermentation. In the previous tutorial, you learned a spreadsheet-based approach for building a simulation model of the yeast-fed batch fermentation. The model was developed through 4 interrelated spreadsheet sections. The first defines the kinetics of the yeast strain used. The second describes the agitation and aeration characteristics of the industrial fermenter. The third performs the numerical integration of the mass balance equations governing the fermentation dynamics. And the fourth presents the simulation profiles of the fed batch process. In the developed simulation model, you can select the main operating variables of the fed batch fermentation: industrial fermenter agitation and aeration conditions, agitation speed N, airflow rate QA, initial fermentation conditions, initial glucose concentration, GLU0, initial biomass concentration, X0, initial volume fraction, V0 over Vt, fed batch feeding conditions, glucose concentration in the feed, GLU feed, target steady-state glucose concentration GLU-SS. The fermentation is terminated either when the fermenter reaches its maximum working volume or when the dissolved oxygen concentration falls below its minimum allowable level. Under the selected operating conditions, the simulation model predicts the dynamic behavior of the fed batch fermentation process. After an initial batch phase lasting several hours, the following behavior is observed: a regulated glucose concentration maintained at 0.2 grams per liter, an exponential increase in biomass concentration resulting from a constant specific growth rate of the yeast, an exponentially increasing feed flow rate required to maintain the steady-state glucose concentration, minimal ethanol production, and a gradual decrease in dissolved oxygen concentration. The fermentation is terminated when the dissolved oxygen concentration reaches the critical minimum value of 1 milligram per liter. The spreadsheet model also predicts the total fermentation time, together with the final concentrations of yeast biomass and ethanol. In this second part of the tutorial on the digital scale-up of yeast-fed batch fermentation, I present a spreadsheet-based approach for optimizing the fermentation process using the simulation model. We will examine the 4 sections of the spreadsheet in sequence: virtual experimentation, oxygen transfer limitations, optimization criteria, and fermentation optimization. The first section of the spreadsheet performs a virtual experimentation on the yeast-fed batch fermentation. Fed batch fermentation is a complex process that depends on the 7 operating conditions defined previously. Spreadsheet-based virtual experimentation enables the rapid evaluation of how these operating conditions influence fermentation kinetics and final product concentrations. It also provides a sensitivity analysis of the input variables, identifying the most influential parameters on which the optimization strategy should focus. Virtual experimentation is most conveniently performed using the spreadsheet data table functionality. With the data table feature, key variables can be systematically varied while automatically calculating the resulting changes in fermentation dynamics. The first approach is the one-dimensional data table, in which a single variable is varied. Here it is used to calculate and visualize the influence of an operating variable on the kinetics of the fed batch fermentation. For example, the one-dimensional data table is used to simulate fed batch fermentation kinetics at 3 steady-state glucose concentrations, GLU-SS of 0.1, 0.2, and 0.4 gram per liter. The results show that GLU-SS is a highly sensitive operating variable in yeast-fed batch fermentation. Increasing GLU-SS leads to faster yeast growth, but a lower final biomass concentration, faster ethanol formation, and a higher final ethanol concentration, and a more rapid decrease in dissolved oxygen concentration, reaching the minimum allowable level of approximately 1 milligram per liter. The data table functionality can also be used to assess the influence of the stirring rate. The yeast fermentation kinetics is simulated at 3 impeller speeds, N equals 40, 50, and 60 revolutions per minute. The stirring rate primarily affects the dissolved oxygen profile during fermentation through its influence on the oxygen transfer coefficient, KLA. Increasing the agitation speed leads to a slower decrease in dissolved oxygen concentration, delaying its decline toward the critical minimum level. Consequently, higher impeller speeds result in higher final yeast biomass concentrations. Similarly, using the data table functionality, the yeast fermentation kinetics can be simulated at 3 volumetric airflow rates, QA of 0.1, 0.2, and 0.5 VVM. The aeration rate primarily affects the dissolved oxygen profile during fermentation through its influence on both the oxygen solubility and the oxygen transfer coefficient, KLA. Increasing the airflow rate leads to a slower decrease in dissolved oxygen concentration, delaying its decline toward the critical minimum level. Consequently, higher airflow rate result in higher final yeast biomass concentrations. In the virtual experimentation section, we also use the 2-dimensional data table functionality. This approach allows the simultaneous evaluation of the influence of 2 operating variables on fermentation outcomes, such as the final biomass concentration or the final ethanol concentration. For example, the 2-dimensional data table can be used to assess the influence of increasing GLU-SS from 0.1 to 0.5 grams per liter at 3 agitation speeds, N of 40, 50, and 60 revolutions per minute. The effects are evaluated on 2 key fermentation outputs. Final biomass concentration, increasing GLU-SS decreases the final biomass concentration, X-fin. Increasing N increases X-fin. Final ethanol concentration, increasing GLU-SS increases the final ethanol concentration, eth-fin. Increasing N also increases ethfin. The second spreadsheet section assesses the limitations imposed by oxygen transfer in the fermenter. In aerobic fermentations, cellular biomass concentration, and therefore fermenter productivity, is often limited by the capacity to transfer oxygen from the gas phase to the liquid medium. It is therefore essential to evaluate the maximum biomass concentration permitted by oxygen transfer that can be achieved in the industrial fermenter. Inside the fermenter, the volumetric oxygen transfer rate Jo 2/3 in gram oxygen per liter per hour from the gas phase to the liquid medium is described by the mass transfer equation Jo 2/3 equals KLA O2 star mean minus O2L, where KLA is the volumetric oxygen transfer coefficient equal to the product of the liquid side mass transfer coefficient KL and the specific interfacial gas liquid area A. O2 star mean is the mean oxygen solubility concentration in the fermenter. O2L is the dissolved oxygen concentration in the bulk liquid phase. The maximum oxygen transfer rate is reached when the dissolved oxygen concentration approaches its minimum allowable value, O2L min, below which the microbial growth rate decreases and undesirable metabolites may be produced. The maximum oxygen transfer rate, denoted as Jo 2/3 max, is therefore expressed by Jo 2/3 max equals KLA O2 star mean minus O2L min. During fed batch fermentation, the oxygen molar fraction in the outlet gas decreases because of the increasing oxygen consumption rate in the fermenter. This results in a gradual decline in the mean oxygen solubility within the fermenter. Consequently, the maximum oxygen transfer rate, Jo 2/3 max, decreases slightly over the course of the fermentation. In aerobic fermentation, a fundamental relationship is the instantaneous oxygen balance in the liquid medium inside the fermenter, which states that at every instant, the volumetric oxygen transfer rate is equal to the volumetric oxygen consumption rate by the microbial cells. Under these conditions, the maximum volumetric oxygen consumption rate that can be achieved is therefore equal to the maximum volumetric oxygen transfer rate in the fermenter. For the yeast-fed batch fermentation, the maximum volumetric oxygen consumption rate is reached when the increasing volumetric oxygen consumption rate, RO 2/3, during exponential biomass growth becomes equal to the maximum volumetric oxygen transfer rate, Jo 2/3 max. At this point, the dissolved oxygen concentration decreases to its critical value, O2L min, below which oxygen limitation occurs. From the maximum oxygen consumption rate, it is possible to evaluate the maximum biomass concentration that can be reached in the fermenter. The volumetric oxygen consumption rate, RO 2/3, is equal to the product of the specific oxygen consumption rate, QO2, and the biomass concentration, X. It can therefore be expressed as the product of the stoichiometric coefficient, YO2 over X, the steady-state specific growth rate, μSS, and the biomass concentration. Accordingly, the maximum biomass concentration allowed by oxygen transfer, X max O2, is calculated as X max O2 equals RO2 third max divided by YO2 over X mu SS. Thus, during fed batch fermentation, the maximum attainable biomass concentration can be increased by reducing the cellular growth rate. In the oxygen transfer limitation section of the spreadsheet, the maximum allowable yeast biomass concentration is calculated as a function of the steady-state glucose concentration, GLU-SS, during fed batch fermentation using a calculation table. The table includes, in the columns, the calculated Jo 2/3 max, μSS, and X max O2, and in the rows increasing GLU-SS values ranging from 0.05 to 0.5 grams per liter. The specific cell growth rate μss is calculated from the growth rate equation as a function of glu-SS. The formulas for Jo 2/3 max, μss, and X max O2 are first established for the initial glu-SS value. The table is then completed by copying the formulas across the remaining glu-SS values. The calculations reveal a sharp increase in the maximum attainable biomass concentration at glu-SS values below approximately 0.2 grams per liter. The third section of the spreadsheet evaluates the performance criteria used to optimize the yeast-fed batch fermentation process. The objective of scale-up is to identify and establish operating conditions that ensure optimal fermenter performance at the industrial scale. In a previous tutorial, a detailed review of the optimization criteria for microbial fermentation processes was presented. For most fermentation processes, the most important optimization criterion is fermenter productivity. In our case, the fermenter volumetric productivity, denoted as Prod-X, is defined as the amount of yeast biomass produced at the end of the fermentation, divided by both the total fermenter volume and the total process time. It is typically expressed in grams biomass per liter hour or kilograms biomass per cubic meter hour. The total process time includes the final fed batch fermentation time, TFB, plus the additional downtime, TAD, required between successive runs for emptying the fermenter, cleaning, refilling with fresh medium, and sterilization before the next fermentation cycle. The final biomass produced is equal to the final medium volume V multiplied by the final biomass concentration X fin. Accordingly, the volumetric productivity is calculated as Prod-X equals Vx fin divided by Vt TFB plus TAD. Productivity thus defined is therefore a direct indicator of fermenter utilization efficiency. For the yeast fermentation, a second important performance criterion is the global sugar-to-biomass conversion yield. For fed batch yeast fermentation, the overall glucose-to-yeast conversion yield, denoted as Yx over glu, is defined as the ratio of the final mass of yeast produced to the total mass of glucose consumed. The latter includes both the glucose initially introduced into the fermenter and the glucose added during the feeding phase. Yx over glu equals Vx fin divided by V0 glu 0 plus M glu added. The mass of glucose added during feeding is determined from the volume of feed medium added, V minus V0, multiplied by the glucose concentration in the feed, glu feed. Accordingly, the conversion yield Yx over glu is calculated as Vx fin divided by V0 glu 0 plus V minus V0 glu feed. Thus defined, the glucose conversion yield measures the efficiency with which yeast convert glucose into cellular biomass during the fed batch fermentation. The ultimate performance criterion for yeast fermentation is the production cost per kilogram of yeast biomass produced. The fermentation cost includes all expenses associated with raw materials, energy consumption, equipment utilization, and labor. Material costs include the nutrients supplied in the medium, primarily the cost of sugar, as well as water and any additional supplements. Energy costs arise from fermenter agitation, aeration, cooling, and fluid pumping. Equipment costs include depreciation, maintenance, and other expenses associated with equipment utilization. Labor costs include the salaries of technicians, supervisors, and engineers, together with general company overhead expenses. Accordingly, the production cost per kilogram of yeast is the sum of the material cost per kilogram, mainly represented by the sugar cost, the equipment cost per kilogram, the energy cost per kilogram, and the labor cost per kilogram. The production cost per kilogram of yeast can be expressed as a function of the two technical criteria, the fermenter productivity prod X, and the glucose-to-biomass conversion yield Yx over GLU. The production cost per kilogram yeast can be written as the sum of the sugar cost per kilogram of sugar divided by yield Yx over GLU, the fermenter utilization cost per cubic meter an hour divided by productivity prod X, the fermenter energy cost per cubic meter an hour divided by prod X, and the labor cost per cubic meter an hour divided by prod X. Because each of these contributions depends either on fermenter productivity or on glucose-to-biomass conversion yield, the overall production cost is directly determined by these two technical criteria. Accordingly, the lowest production cost is achieved when the fermenter operates under conditions that simultaneously maximize productivity and maximize sugar-to-biomass conversion yield. Optimal fermentation operation therefore requires both high productivity and high conversion yield. In the fed batch spreadsheet, the two optimization criteria, productivity prod X and sugar-to-biomass conversion yield Yx over GLU, are calculated from the final volume fraction V over Vt and the final biomass concentration X fin as functions of the operating variables. Their values are displayed in the extended final results row of the spreadsheet. The final fermentation optimization section of the spreadsheet determines the optimal operating conditions for yeast-fed batch fermentation in the industrial fermenter. The objective is to identify the fermentation conditions that maximize the previously defined optimization criteria: fermenter productivity and glucose-to-biomass conversion yield. The 7 operating variables to be optimized are the impeller stirring rate N and airflow rate QA, the initial glucose concentration GLU0, biomass concentration X0, and medium volume fraction V0 over Vt, the glucose feed concentration GLU feed, and steady state concentration GLU SS. For industrial fermenter agitation, the highest possible impeller stirring rate N is generally preferred in order to maximize the oxygen transfer coefficient KLA and, consequently, the attainable biomass concentration. However, in large-scale fermenters, the rotation speed is limited to avoid exceeding a volumetric agitation power of approximately 1 kilowatt per cubic meter and an impeller tip speed of approximately 10 meters per second for the 100 cubic meter industrial fermenter considered here. The impeller rotation speed is therefore set at approximately 60 revolutions per minute. For fermenter aeration, a high airflow rate QA is preferred in order to maximize oxygen solubility and the oxygen transfer coefficient KLA. However, the aeration rate should not be excessively high to avoid fermenter flooding and excessive foaming. For the industrial fermenter considered here, the volumetric airflow rate is set at 0.5 VVM. With respect to the initial fermentation conditions, the initial glucose and biomass concentrations are relatively insensitive operating variables. To maintain a short initial batch phase, they are set at 1 gram per liter for GLU0 and 0.2 grams per liter for X0. In contrast, the initial medium volume fraction V0 over Vt strongly influences the fermenter filling time and, consequently, the duration of the fed batch phase. The initial volume fraction is therefore carefully adjusted so that the time at which the fermenter becomes completely filled coincides with the moment when the dissolved oxygen concentration reaches its minimum allowable value. This ensures that the maximum biomass concentration permitted by oxygen transfer is achieved precisely when the fermenter reaches its full working volume. This operating strategy enables efficient utilization of both the fermenter capacity and the available aeration capacity. To ensure that the fermenter filling time, T-fin, coincides with the moment when the minimum dissolved oxygen concentration is reached, the initial medium volume V0 is selected so that the total amount of glucose added during the fermentation matches the glucose required for the expected biomass production. The total glucose mass supplied during the process consists of the initial glucose mass, V0 glu0, and the glucose added during feeding, Vt minus V0, glue feed. The total glucose required for biomass production is determined from the stoichiometric coefficient, Y glue over X, multiplied by the total biomass produced at the end of the fermentation, when X reaches X max O2. By equating these two glucose mass expressions, the required initial volume fraction, V0 over Vt, can be determined. Neglecting the contributions of the initial glucose and biomass concentrations, the relationship becomes V0 over Vt equals 1 minus Y glue over X, X max O2, divided by glue feed. According to this relationship, the optimal initial volume fraction, V0 over Vt, increases with increasing glucose feed concentration, glue feed, and with increasing steady-state glucose concentration, glue SS. During the fed batch feeding phase, the steady-state glucose concentration, glue SS, is the most sensitive operating variable. It directly governs yeast growth and metabolic activity and strongly influences the final biomass concentration, ethanol production, and fermentation duration. The simulation model using the optimal initial volume fraction, V0 over Vt, is therefore used to assess precisely the influence of glue SS on fermenter productivity prod X and glucose-to-biomass conversion yield Yx over glue. The simulations are performed using an optimization table that includes, as columns, the calculated X fin, ETH fin, V0 over Vt, T fin, prod X, and Yx over glue, and as rows, increasing glue SS values ranging from 0.05 to 0.5 grams per liter. The formulas are first established for the initial glue SS value, and the remaining table results are then obtained by copying the formulas across the subsequent values. According to the simulation results obtained at a fixed feed glucose concentration of 200 grams per liter, the final biomass concentration increases strongly as glue SS decreases due to the reduction in the specific oxygen consumption rate. But this is accompanied by an increase in the fermentation time T fin, resulting from the lower cellular growth rate. As a consequence, reducing glue SS leads only to a slight increase in fermenter productivity. The highest productivity, approximately 0.63 kilograms per cubic meter hour, is obtained for glue SS values below 0.1 grams per liter. The same simulations show that the final ethanol concentration increases with increasing steady-state glucose concentration, glue SS. As a consequence, the glucose-to-biomass conversion yield Yx over glue decreases as glue SS increases. The highest conversion yield, approximately 0.48 grams biomass per gram glucose, is obtained at low glue SS values below 0.2 grams per liter. During the fed batch feeding phase, an additional important operating variable is the glucose concentration in the feed, glue feed. This parameter strongly influences the feed flow rate, the initial medium volume fraction, and the final fermentation time. The influence of glue feed on fermenter productivity and glucose conversion yield is thus precisely assessed using a one-dimensional data table. The table includes, in the columns, the calculated values of fermenter productivity, prod X, and glucose-to-biomass conversion yield Yx over glue, at glue SS equals 0.2 grams per liter. And in the rows, increasing glue feed concentrations ranging from 50 to 400 grams per liter. According to the data table simulations, the fermenter productivity prod X increases slightly with increasing feed glucose concentration, glue feed, until reaching a maximum value at concentrations above 300 grams per liter. Whereas the glucose-to-biomass conversion yield Yx over glue at a fixed glue SS remains essentially independent of glue feed. The model-based simulations performed in this spreadsheet section make it possible to identify the optimal operating conditions for yeast-fed batch fermentation using the selected Saccharomyces cerevisiae strain. The optimal conditions are a stirring rate N of 60 revolutions per minute, an airflow rate QA of 0.5 ppm, an initial glucose concentration GLU0 of 1 gram per liter, an initial biomass concentration X0 of 0.2 grams per liter, an initial medium volume fraction V0 over Vt of approximately 0.82, a feed glucose concentration GLU feed of 300 grams per liter, and a steady-state glucose concentration GLU-SS of 0.1 grams per liter. Under these optimal operating conditions, the yeast-fed batch fermentation exhibits the following dynamic behavior and final process characteristics. After a short initial batch phase, the glucose concentration is maintained at a constant value around 0.1 grams per liter. A final fermentation time of approximately 36 hours is achieved, corresponding to the point at which the fermenter becomes completely filled, while the dissolved oxygen concentration simultaneously reaches its minimum allowable value, an exponential increase in biomass concentration, ultimately reaching approximately 25 grams per liter, and negligible ethanol production. These optimal operating conditions ensure both a high fermenter productivity Prod X of approximately 0.64 kilograms per cubic meter an hour, and a high glucose-to-biomass conversion yield YX over GLU close to 0.48 grams biomass per gram glucose. In summary, in this tutorial, you learned how to use a spreadsheet model to optimize a yeast-fed batch fermentation process digitally. Step by step, you perform virtual experiments using data tables to evaluate the influence of operating variables on the dynamics of the fed batch fermentation. You determine the maximum yeast concentration permitted by oxygen transfer within the industrial fermenter. You also evaluated two key performance criteria: fermenter productivity and the glucose-to-biomass conversion yield. Finally, you optimize the operating conditions of the fed batch fermentation to achieve both high fermenter productivity and high glucose conversion efficiency. If you would like to explore this further, you can deepen your understanding of spreadsheet-based simulation modeling by enrolling in one of our 2 online courses, Digital Scale-Up and Optimization of Microbial Fermentations, and Simulation, Scale-Up, and Optimal Operation of Microbial Fermentations. For further information, please visit our Bioprocess Engineering online website or contact us at bioprocessdigital.com. We hope you found value in this introductory tutorial on bioprocesses. Your feedback is important to us, so please share your comments with us. Explore our website for more information about our comprehensive online courses in bioprocess engineering, and be sure to subscribe to our Bioprocess Engineering online channel for upcoming tutorials. Thank you for watching.